The main hero of my talk is the Rademacher case. And the first thing I would like to say is that this is joint research. It is the results of joint research with Kostya Lykov. He is work now in Belarusian State University, Minsk. And here I would like to talk about the result of our two recent papers. The first paper is very recently published, and the second paper is preparation. Okay, and I would like to talk the main point. I would like to talk. It is a description of symmetric spaces, such that Rademacher case and some related systems are equivalent in X to the classical to the canonical basis EK in L2 basis. And if I will have a time, I would like to touch also some connections, unexpected connections between unconditionality, some properties of the Rademacher case, and the discrepancy of set systems. Okay. Let me start, please, with the definition of Rademacher system, and the famous Hinton inequality. The Rademacher system, here you see one of the definitions of Rademacher system. You see that this system are some signs of sinus. This is very simple functions which take only plus minus. And in other words, this sequence is just a sequence of identically and symmetrically distributed functions, independent functions, taking values plus minus 1. Okay, and now maybe the more important fact from theory of this system is the famous Hinton inequality. Hinton inequality says that for every p, for every finite p, there exists a constant Cp less than square root of p, such that for any real AK, we have this two-sided inequality. This inequality then means that the norm of linear combination of Rademacher functions in LP for every p is equivalent to the canonical basis of L2. It is a very fundamental fact which very often used in probability theory and theory of functions, in geometrical theory of Banach spaces. This means that Rademacher function, the sequence of Rademacher function is equivalent in every LP with finite p to the canonical basis of L2 for each p. But constants, of course, depend on p. At the same time, if we take L infinity, we will see that it is a very easy fact. The norm of the sum of the linear span of Rademacher function L infinity will be the norm of coefficients in L1. And with jump between LP with finite p and L infinity cannot be explained if we live in the scale of LP spaces, And this is a good motivation to consider Rademacher function is a more general scale of symmetric spaces. And now I should recall some very basic definitions from theory of symmetric spaces. And the first, it is two measurable functions, x and y, are called equimeasurable if we have with an equality for distribution function of absolute value of these functions. Here mu is the usual Lebesgue measure. And for instance, for each measurable functions x, there exists decreasing left continuous non-negative function x star, rearrangement of this function x, which is defined by this formula. Okay. And a Banach space of measurable functions is of measurable functions on the segment 0, 1, only on the segment 0, 1, is called symmetric space if the following properties hold. The first means that x is a Banach lattice, that is, if for every functions x, y, such that absolute value of x, y is less than absolute value of x, and x from x, it follows that y belongs to x also, and has the smaller norm. And the second property means that if x and y are equimeasurable, or other words, the distribution functions of absolute value of x and absolute value of y are the same, then, and x belongs to x, then y belongs to x also with the same norm. And one more property which will be used for us is that there are the smallest symmetric of rearrangements in space. It is L infinity, and there is also the largest space L1. Every arrangement means every symmetric space X is located between L1 and L infinity. Okay. And now some many classical spaces are symmetric. For example, Lorentz spaces, Marcinkiewicz spaces, and Orlich spaces. Next, for me, will be important only Orlich spaces. So I very shortly recall their definition. If M of U is the Orlich function, this means that this is a convex increasing continuous function on the semi-axis 0 infinity, such that M0 equals 0. Then Orlich space consists of all measurable functions on the segment 0, 1, such that this norm, Luxembourg norm, is finite. Of course, if we take for M power function u to the power p, then we obtain that Lm is Lp isometrically. But for us will be more important another class of Orlich function, the so-called exponential Orlich function XPLR. It is also classical spaces, and XPLR, it is the Orlich space LNR, such that NR is the Orlich function, any Orlich function, which is equivalent to the function e to the power c. C is some constant, u to the power r for large u, With spaces, with exponential Orlich spaces, are the spaces which are close to L infinity. to the smallest arrangement invariant space. These spaces are not are non-separable, and there is also more transparent characterization of these spaces, namely X belongs to this space, expel R, if and only if this supremum is finite. This characterization shows that in this space there is functions which have the largest rearrangement, and the largest rearrangement is just log to the power 1 over R, E over U. Okay, these spaces, as I said above, non-separable, but if we take GR, GR is only notation, and GR is closure of L infinity in this space, expel R, then this space GR will be separable, and X belongs to GR if this limit equals 0. This limit equals 0. This is the same expression, and this characterization of the above characterization of expel R. Of course, GR is some subspace of expel R. These spaces will be important in the Rademacher theorem. Rademacher theorem answers the question I was formulated above, in which the problem is in which symmetric spaces Rademacher functions sequence of Rademacher function is equivalent to the canonical L2 basis, and this theorem, due to Rodin Simonov, gives the complete answer to this question. Let X be a symmetric space, then the Rademacher sequence is equivalent to the canonical basis. Ek is always throughout in my talk, it is the canonical basis in L2 is equivalent to this canonical basis in L2. If and that is with some constant, we have this relation. This relation with sign means the two-sided inequality precisely as in the Hinton inequality. The Hinton inequality, that is the Hinton inequality in the space X. If and only if X contains the space G2. G2, it is a separable part, the closure of L infinity in the expel 2 when I defined here. So this theorem shows that the G2 is the smallest symmetric space, such that the Hinton inequality holds in this space, in the smallest symmetric space in which we have Hinton inequality. So it is a very clear answer to the question in which symmetric spaces this Rademacher function span L2. So the Rademacher function span L2 in almost all symmetric spaces up to G2 for NLP and some other spaces, and only for spaces which are close to L infinity, it is not the case. It is not the case. Now, I would like to jump from Rademacher function to the Rademacher chaos. What is the Rademacher chaos? What is the chaos? Informally, for the chaos generated by some sequence, it is just the sequence of formed by products of the function from this sequence. It is very simple thing. More precisely, if we say about Rademacher function, we take some d. D is some positive integer. Then by delta d, we denote the lower triangle of the Cartesian product n to the power d. That is, delta d contains from all multi-indices from nd, such that the entry is strictly decreasing, as we have here. And so for every multi-index, we set this function. This function both are j with a row t is if this is the product of Rademacher function with entries as indices, and this sequence of this both r j is called homogeneous Rademacher chaos of order d, because of each product contains of d terms. Okay. What is can say about this sequence? By the way, the first paper about Rademacher chaos was due by Norbert Wiener and then some joint paper by Wiener and Wintner at approximately in 1945. This paper was published a very long time ago, and this sequence Rj is orthonormal, uniformly bounded system on segment 0, 1. This is some subsequence of the classical Walsh system, the Walsh system. But this system is not independent, in contrast to the Rademacher functions. And this is even not multiplicative system, because there is, we can take some combination, some product of these functions, such that the integral from the product of this function doesn't equal to 0. But we see, however, many properties of this system resemble the properties of independent uniformly bounded functions. And a good reference for theory of this of Rademacher house is the book by Kvapin and Wojcinski, for example. There is also some other books also. And I would like to say only about the one result, one inequality, Bonamy or Bonamy and Bonamy-Kinner inequality, which shows that Rademacher chaos of arbitrary order satisfies the Hinton type inequality. That is, the Rademacher chaos of the n-year order spans in LP, with, of course, with finite p, L2 is equivalent to the canonical basis in L2. It's okay. It's the same as the system of Rademacher system. Now, what is about Rademacher, how the Rademacher chaos, or property Rademacher chaos in symmetric spaces? It is our first question which was interesting for me a long time ago, and I tried to prove the result similar to the Rademacher Semyonov theorem, and I proved a long time ago, you see, the following result. Let X be a symmetric space, then the following three properties are equivalent. The first property is that RG, it is a result only for second order Rademacher chaos. The second order Rademacher chaos is equivalent to the canonical basis in this space X, if and only if this sequence is unconditional in X. A little bit later, I will talk about unconditionality and some unconditionality type properties. And the third property, X contains G1. You see that in Voronezh Semyonov theorem, we the space G2 had arisen. Here, G1. G1 is wider than G2. So this condition is more restrictive than if X contains G2, but it's not strange because of we say here not for Rademacher function, we say here for Rademacher chaos of order 2. And so we have here more restrictive condition, a little bit more restrictive condition. Okay, and maybe more interesting here that the property, strong property of equivalence of Rademacher case to the canonical basis of L2 is equivalent to the much weaker condition of unconditionality of this sequence, unconditionality of this sequence. Because it is interesting that Rademacher system, the behavior of Rademacher system in symmetric spaces is completely different. It is known, for example, that for every interpolation space, sequence space between L1 and L2, small L1 and small L2, we can find some asymmetric space such that Rademacher function will span in this space with space which is equivalent to this space. For example, we can find symmetric spaces in which Rademacher function span LP when P between 1 and 2, strictly between 1 and 2, for example, and so on. The other system. For Rademacher chaos situation completely different. Or L2 or either with sequence spans L2, or this sequence is not unconditional. And the second result I would like to say about it is the result due to Ron Bley and his PhD students at that time again, which found very precise relationships between the property of combinatorial dimension of a set in index A and the properties of the following subsequence of Rademacher chaos, which correspond to this index set in Orlich spaces. So when we knew about this result, there was arising a hope to find some. Oh, sorry. Okay. Some connections between to find some connections between the combinatorial dimension of an index set and the properties of Rademacher case in symmetric spaces. And there is the following question: to what extent does the combinatorial dimension determine properties of the Rademacher case in symmetric spaces? And now I would like to say about combinatorial dimension. Combinatorial dimension. First, informally, if we say about combinatorial dimension, we should say that the concept of combinatorial dimension shows allows to measure the density of sets from the point of view of presence of a Cartesian product structure in these sets. This concept was introduced and developed by Ron Bley, and the best reference for familiar with this concept, to know many things about this concept. It of course his monograph, very remarkable book. And now I would like to say that we use with Kostya the following modification of this concept, considering the lower and upper estimates separately in this for this constant for this concept. More and namely, let alpha is bigger than 1. A set A from Cartesian product n to the power d is a super alpha set if for some constant Ca there exists a number n, there are sets Bj, the number of elements of Bj equals n, j from 1 to d, such that we have this inequality, this lower estimate. This estimate means that the index set A contains some spaces which resemble Cartesian product structure, and the density of this Cartesian product is not less than to the power n to the power alpha. It is a lower estimate for cardinality of such special subsets of A. And similarly, we can prove also, we can define also the concept of upper beta set, of sub beta set. We have here upper estimate, the following upper estimate. Okay, if a set A which has both which is both super alpha set and beta set and sub beta set, he holds alpha beta set. And in the case when alpha equals beta, alpha set, we have that this set has exact combinatorial dimension alpha. It is a very important fact that for every alpha from 1 to d, there exists a set of exact combinatorial dimension alpha, and this fact is proved by using a, in general, by some random procedure. But if the number alpha is rational, we can also define some deterministic procedure to find the set with such combinatorial dimension. This is the simplest example. If D equals 3, then we can define index set with exact combinatorial dimension 2, in which in the following here, it is A is a collection of these triples with properties, and it is one can easily check that this subspace has combinatorial dimension 2. For this example is more complicated, and here we define subset which has exact 3/2 finite exact combinatorial dimension 3/2 set from n to the power 3, n to the power 3. Okay. And now I said above that for second order Rademacher chaos, we have the equivalence of L2 canonical base L2 basis of Rademacher chaos to the property of unconditionality of this sequence in X, and it turned out that this condition, instead of unconditionality, we can say here even for a more weaker property, and I would like to define these properties which are weaker than unconditionality property. This is system, the concept of system of random unconditional convergence and divergence. Informally, unconditionality means that unconditionality of a basic sequence means that the some stability of properties of this sequence when we multiply the elements of this sequence by signs plus minus 1. And more precisely, a basic sequence Xn in a Banach space X is unconditional if there exists some D such that for any n and for any signs theta a, we have this inequality. That is the norm of linear combination after multiplication of all coefficients to signs. The norm of this linear combination in X is the same as without multiplication up to some constant. And the following wiki properties, when the average of over signs replaced maximum or minimum over signs, was introduced by Billard, Kvapin, Pilchinsky, and Samuel. Namely, a basic sequence Xn in a Banach space X is called a system of random unconditional convergence, in short, Rook system, if there is a constant D such that for all n and for all k, real k, we have this inequality. Here Rk are usual sequence of Rademacher functions. So we have here on the left side the average of the sums by multiplication of signs, and the average is taken over signs. And in the similarly, we can define also the system, a system of random unconditional divergence, root system. This system, in this case, we replace the right-hand side part in unconditionality by average. There is an easy fact that a basic sequence is unconditional if and only if it is root and root, has root and root property. And now I would like to formulate some main results. The first results show that under certain non-restrictive density condition on an index set A, with a subsequence of Rademacher chaos corresponding to this index set is equivalent to the canonical base in L2 if and only if this system has root property. Theorem 1. If X, let X be a symmetric space, and D from N, and if assume that X A is some subset of delta D, and this subset is alpha beta set, such that this sum is bigger than, strictly bigger than 2. Then the following conditions are equivalent. Here you see 3 conditions. And the first condition is that this system is root. The second, that it is unconditional basic sequence in X. And the third, that this condition is equivalent to the canonical basis in L2. I remark that, of course, implications from B implies A and C implies B are obvious. And the only implication which is should be proved is that A implies C, because of course A is much weaker than C. And here is stated some corollary of this theorem, which contains some sufficient conditions on A, showing that the inequality alpha plus 1 over beta is bigger than 2 is non-restrictive. Here we see some sufficient conditions, and I would like to say about only the last, because of, in particular, if this is true, the equivalence of A, B, C is true if A has exact combinatorial condition alpha bigger than 1. Exact combinatorial condition bigger than 1. Of course, if alpha equals beta here, and alpha is bigger than 1, then alpha plus 1 over alpha is bigger than 2, which is a very easy inequality. Okay. And now the second result for Orlic spaces. In the case of Orlic spaces, this result, theorem 1, can be essentially refined. For Orlic spaces, if we know that A has exact combinatorial dimension alpha bigger than 1, then the following conditions are equivalent. A, B, C is the same as in theorem 1, only for Orlic spaces. And here we see also the fourth condition. LM contains the space G2 over alpha. So all these condition 1, A, B, C can be characterized by this embedding. This embedding shows that the combinatorial condition precisely determines the smallest space for which this sequence is equivalent to the canonical basis. So we obtain here the theorem for this more complicated case, similar to the Rodin-Semyonov theorem and for Bonami-Keener result, because principal issue is here that everything is determined by combinatorial dimension. Combinatorial dimension precisely determines the rate, the smallest symmetric space for which we have generalized Hinchen inequality. And the third theorem is the theorem when, in the partial case, when A is equal to the whole delta to the power D. That is the case when we say about full Rademacher case, full Rademacher. In this case, when we consider full Rademacher case, these properties, 1, A, B, C, with all these properties, 1, 2, 3, is equivalent to the following embedding. Okay. And now I have 10 minutes. So I would like to say about root property, because of we see in this theorem that the root property, we know in which symmetric spaces we have root property, because of the easy consequence from this theorem that this result that n symmetric space, the full Rademacher case of arbitrary order has the root property in a symmetric space X if and only if X contains the space G with 2 over D. So we have complete answer in which symmetric spaces we have root property thanks to this result, thanks to this consequence. What is about root property? It turns out that the root property much more tricky than the root property. And now I would like to say about some result we have. The first result is due to Kvapin-Pilchinsky, Samuel. They prove that the whole wall system has the root property in G2. In particular, of course, and the Rademacher chaos has this property in G2. Later, Dot, Semyonov, and Sukachev proved that every orthonormal uniformly bounded sequence in a separable symmetric X has the root property in X if and only if X lies between exp L2 and L2 and L2. And then we recently with Lykov proved a little bit more precise result. We result namely for Rademacher chaos. We proved that Rademacher chaos has the root property in a symmetric space X if X contains the space XL2. That is in this for this space we have this inequality. Inequality is root property of the space of this system. Here RJ, it is usual Rademacher J with arrow is a usual Rademacher sequence for averaging. The sequence for averaging here. Okay. And now I would like to say about some remark. The point is that for if we take the Rademacher sequence with signs multiplied Rj by some signs, this sequence J Rj is identically distributed with the same Rademacher sequence, and so we can rewrite this inequality in the a little bit different form. On the we have this equality. So multiplication by signs doesn't change with expression, and so we can rewrite the inequality for root property of Rademacher chaos in the same way. We can put on the left hand side minimum over signs. So root property means that the minimum is equivalent to the average, because of course minimum over signs is less than average, but for root system these expressions are equivalent. And now the question 1, to find the characterization of symmetric spaces X for which Rademacher chaos has a root property in X. We don't know the answer to these questions, and maybe this question is not easy, and maybe firstly it is necessary to solve a little bit easier problem to investigate the Rademacher chaos in infinity. Consider this question 2. Is the Rademacher chaos is a root system in infinity or not? And maybe if it is not, that to find some as large as possible the set of coefficients for which we have the root property. This question there are some different motivation for importance of this question. The first is that if we take decoupled Rademacher chaos, because of in usual Rademacher case, maybe you remember, all terms, all Rademacher functions depend on one variable. But in the decoupled Rademacher case, you see here terms, Rademacher functions depend on different variables. But decoupled, many properties of decoupled Rademacher cases are similar to the properties of genuine Rademacher cases. And if we take the norm of this second order decoupled Rademacher case in L infinity, it is one can easy to check that this norm is equivalent to the norm of matrices of coefficients. Matrix of coefficients is considered as a, in an obvious way as operator, and the norm of this operator in L infinity to L1 is the same as the norm of this decoupled case. Okay. And there are some partial results. Maybe I skip this. It is interesting that the theory of Rademacher cases is connected some unexpected way with discrepancy of set systems, or in other terminology of hypergraphs. I remember with discrepancy of, but now maybe it's better to finish because of I have no time. Thank you very much for your attention.